Welcome back, hello, and Selamat Hari to everyone. As you can see, I'm recording this very high radio. So, Muhammad Alif Aiman here, matrix number U2004961. Back again to talk about my experiments. Today, we are going to talk about bipolar junction transistors, or BJTs. So, quick introduction about BJTs. They are about the same as a diode, but instead of having two semiconductors, they have three. And there are three pins on the transistor, which are called a collector, a base, and a emitter each. As the name suggests, the collector collects a current, and the emitter emits a current. But the base actually acts as an amplifier mostly, and it's just a thin layer sandwiched between the emitter and the collector. Also, BJTs amplify some currents by way of recombination of carriers from the base and the collector. The base is purposely made thin to avoid the carriers from it from going back and leaking back into the input. Also, one thing to note, BJTs also have a breakdown voltage, such as diodes. So, if the voltage supplied is more than the threshold that it can hold, then the BJT will break down. Though there are many configurations of the BJT, but for this experiment, we will be only focusing on how to determine the quiescent operating conditions of the voltage divider bias BJT configurations, and to measure AC and DC voltages in a common emitter amplifier. So, let's get started. So, for part 1, the circuit is built like this, and it only focuses on how to find the beta value of the 2N3094 BJT. Also, in Easy EDA, there's no model of 29394 BJT, so you have to change the model there by just changing the name of the model. Here, the beta value represents the ratios of application of collector current by the current of the base of the BJT, which is shown by this formula right now. Also, moving forward, this beta value will be the same as the BJT is used throughout all of the experiments. In part 2, we used the BJT and set it as a voltage divider configuration, shown as the circuit now. And by placing it in a circuit like this, the results were calculated with two methods, one using the measured voltages, and the other one using the beta values. Now shown will be the beta values and using the voltage circuits. As you can see, there are like slight variations between the two, because when in voltage divider configuration, the BJT is not dependent from the beta anymore. So when using the beta value, the calculated values will not be as accurate as anymore. To find the quiescent operating conditions, or much commonly known as a Q point, we must find the current of the collector IC and the voltage of the collector VC. And the point where they intersect is the Q point, shown in the graph like now. This is not an actual representation of the graph of this BJT, but this shows a general graph of how a BJT works and how the Q point is found. So the determined Q point of our BJT is 1.613 times to the power of 10 negative 3 and 3.543. So before we delve into part 3, we need to know what a common emitter of a BJT means. So the emitter is common between input and the output. The input is applied between the base and the emitter, while the output is taken between the collector and the emitter. This configuration has the highest current and power gain among all of the three configurations that I stated before. The reason is because the input is at forward bias junction, so its input impedance is very low, while the output is taken from reverse bias, so its output impedance is very high. Moving on to the results for part 3, a graph was made to see the voltage at the base, collector, and the emitter. As we can see, the base has a very small voltage, and the collector has the voltage amplified by a factor of 160, and the wave is also inverted, which follows the theory that the output will be impaired, which is why the source is inverted. The emitted voltage also changed from AC to DC, as in to alternating current to a direct current. The DC output was determined to be 1.6 volt, which is the same for the max speed of the voltage at the collector. So the experiments have all been done. Now we move on to the daily use and real life applications. As you can see from part 3, the BJT is used to amplify the input and change it from an AC source into a DC source in the emitter. Also, the amplified waveform is very useful in communications, for when you get a very low signal of sound from, let's say, in the sea, and we use it a BJT to amplify it, so we can make it more audible for experiments or deep sea scavenging. Also, again for communications, maybe you'll get a very low noise, low sound, and you want to amplify it for to hear it much more clearly. Again, BJTs are very much useful in daily life. Also, not illustrated in this experiment, a BJT can also be used as a switch, which I will show now. So let's head on to that. So here is a simple circuit I made using the LED from a previous experiment, as shown now. The circuit is actually complete as the voltmeter is actually showing a value, but since the collector actually does not collect a lot of current, and as we all know, current tries to go to the path of least resistance, and for exaggeration I use a 100 ohm resistor here and a 100k resistor here. Even though this is still the path of least resistance, there's not a lot of voltage going through, which does not make the LED light up. And we run it again, we see that the value of the LED, the voltage value of the LED goes up, and which in turn makes the LED light up in red. Here you can see it. So this shows that how the transistor acts as a switch, and even though the circuit is complete, it will not be enough to actually supply voltage, enough current for the electronic device such as a lamp to activate, or maybe a bell. And this system is used in fire alarms. So let's say when heat is going up and the temperature sensor hits a certain threshold, then the switch will be activated. So to conclude this experiment was done in a simulator like my experiments before, because we can't be in the lab right now because it's still COVID. And in real life, this experiment will have about maybe a 10% error max, because the temperature of a room which it was done in will affect how the transistor operates, as transistors are electrical components and heat will degrade them. And to end it off, simulators are not a very good metric to see how our electrical components will behave in real life. So see you in the next experiment.